Good morning to all. I am Arthi, Assistant Professor in Welltech Multitech, Dr. Rangaraj and Dr. Sakuntala Engineering College in the Department of Artificial Intelligence and Data Science. Now, I am going to present the topic of minimum spanning tree using greedy technique in design and analysis of algorithm. First of all, we have discussed about what is design and analysis of algorithm. It is used to creating efficient solution to computational problems and evaluating their performance. Design and analysis of algorithm to analyze their efficiency in learning of time and space complexity. Now we have discussed about the greedy techniques. It is the algorithm used for solving the problem by choosing the best option open at the moment. This technique does not focus on the optional result, whether the current result will impact the potential output or not. It is the basic technique to solve the problems in the current best solution of the problem. The minimum spanning tree is a subset of the edges in a connected, unconnected graph that connects all the vertices together without any cycles and with the minimum possible total edge weight. It is used in optimization problems where you need to minimize the cost of connecting all nodes in a network. The applications of minimum spanning tree is the design the network for minimizing the cost of the network, cluster analysis, and approximation algorithm for NP complex problems. Here the properties of spanning tree. First one is the number of vertex in a graph and the spanning tree is same. For example, the vertex of the graph is 5 and the spanning tree vertex is also 5. That means the spanning tree does not miss any vertex in the graph. The second one, there is a fixed number of edges in the spanning tree, which is equal to 1 less than the total vertexes E equal to B minus 1. Here the total vertex is 5. Then the spanning tree edges will be 5 minus 1, 4. The spanning tree should not be disconnected as there should only be a single source of component, not more than that. The spanning tree should be a cycle, which means there would not be any cycle in the tree. The total cost of spanning tree is defined as the sum of edge weight of all the edges of the spanning tree. There can be many possible spanning trees for the graph. In a greedy technique, we have to use two algorithms to find minimum spanning tree. First one is Prim's algorithm and second one is Kruskal algorithm. First of all, we have to see about the Prim's algorithm. This algorithm always starts with single node and moves through several adjacent nodes in order to explore all the connected edges along the way. It builds the minimum spanning tree by start with arbitrary vertex and grow the tree one edge at a time by always choosing the smallest edge that connects a vertex inside the tree to one outside. Here the procedures for Prim's algorithm find the minimum spanning tree. First step, determine an arbitrary vertex as a starting vertex of a minimum spanning tree. Step 2, follow step 3 and step 5 to tell where the vertex that are not included in the minimum spanning tree. Step 3, find edges connecting any tree vertex with the vertexes. Step 4, find the minimum among these edges. Step 5, add the chosen edge to the minimum spanning tree if it does not for any cycle. Step 6, return the minimum spanning tree and exit. Now we have to see the example in Prim's algorithm. Then there is the 9 vertices starting from 0, 1, 2, 3, 4, 5, 6, and 8. They are having different its weights 4, 8, 11, 8, 7, like this. And then step 1. Firstly, we select the arbitrary vertex that act as the starting vertex of minimum spanning tree. Here we have select vertex 0 as the starting vertex and find its neighbor vertexes 1 and 7. All the edges connecting in incomplete minimum spanning tree in other vertices are in the edges 0, 1 and 0, 7. Here 0, 1 and 0, 7 has the different weight. 0, 1 has a weight as 4, 0, 7 has a weight as 8. So we select minimum weight 0 to 1 as a minimum spanning tree node. So include the edge and the vertex as 1 in the minimum spanning tree. Step 3. The edges connecting the incomplete minimum spanning to other vertices 0, 7, 1, 2, and 1, 7. Here the minimum weight is 8. We have to select either 0, 7 or 1, 2. We select here as 0, 1. Step 4. The edges that connect the incomplete minimum spanning tree with the frequent vertices 1, 2, 1, 2, 1, 7, 7, 8, 7, 6. Here the minimum weight is 1. So we have to select 7, 6. Now the connected vertices in the minimum spanning trees are 0, 1, 7, 6. Now we have to find the new node to connect in minimum spanning tree. We check 0, 2, 7, 8, 6, 5, and 6, 8. Now 1, 2 is the weight, their weight is 8. 7, 8 weight is 7. 6, 8 weight is 8. 7, 5 weight is 2. Here 2 is the minimum weight. We have to connect 6 to 5. Again we check the minimum weight to connect the node. First we have to find 1, 2 is 8, 7, 8 is 7, 6, 8 is 6, 5, 2 is 4. So we have to connect 5 and 2 weight of 4. And then check the any cycle is formed in the loop. The connecting edge between the incomplete minimum spanning tree, the other edges are 2, 8, 2, 8 is weight 2, 3, 2, 3 weight is 7, 5, 3 weight is 14, 5, 4 weight is 10. So the minimum weight is 2. You have to connect 2, 8. See here the edges 7, 8 and then 2, 3 both are the same weight or is 7. But we have to connect 7, 8. Here we form a cycle in the minimum spanning tree. We have to avoid a cycle. We have to connect 2, 3 as a minimum spanning tree node. Finally, the vertex 4 remains to be included. The minimum weight of the edge includes, we have to check them 3, 4 as 9, 5, 4 as 10. So we have to select 3, 4 is the minimum spanning tree node to connect. Final structure of minimum spanning tree as follows, and the weight of the edges in the minimum spanning tree as 4, 8, 1, 2, 4, 2, 7, 9 equal to 37. 0 to 1 have a weight of 4, 0 to 7 have a weight as 8, 7 to 6 has a weight as 1, 6 to 5 has a weight as 2, 5 to have a weight as 4, 2, 8 have a weight as 2, 2, 3 have a weight as 7, 3, 4 have a weight as 9. There is no cycle will be formed. The edge count is 1, 2, 3, 4, 5, 6, 7, 8. It's a vertex minus 1. The vertex is 9. The edge count is 8. So all condition will be satisfied for the minimum spanning tree. Then we see Kruskal algorithm. In Kruskal algorithm, sort all edges of the given graph in increasing order. Then it keeps on adding new edges and nodes in the minimum spanning tree if the newly added edges does not form a cycle. It picks a minimum weighted edge at first and a maximum weighted edge at last. This we can say that it makes a locally optimal choice in each step in order to find the optimal solution. It is one of the greedy technique applied to the algorithm. Kruskal algorithm is simple and more efficient when compared to Prim's algorithm. Procedures for Kruskal algorithm. Sort all the edges in increasing order for their weight. Pick the smallest edge. Check if it forms a cycle with the spanning tree formed so far. In the cycle is not formed, then include this edge, else discard it. Repeat step 2 until there are all the vertices are connected and the edge count is p minus 1 vertex, total vertex minus 1. Now we have to see the example. Here there are 9 vertices 0, 1, 2, 3, 4, 5, 6, 7, 8. Each vertex connect to the other vertex and it is a weighted graph. Weights are 4, 14, 18, 11, 2, 7, 1, 6, 19 like that. First, weights of the graph are connected in an increasing order. So they are connected vertices. Here, vertex 7 and 6 have a weight as 1, 8 and 2 have weight as 2, 6 and 5 have weight as 4, 0 and 1 have weight as 4, 2 and 5 have weight as 4, 6 and 8 have weight as 6, 2 and 3 have weight as 7, 7 and 8 have weight as 7, 0 and 7 have weight as 8, 1 and 2 have weight as 8, 3 and 4 have weight as 9, 5 and 4 have weight as 10, 1, 7 have weight as 11, 3, 5 have weight as 14. Step 1. Pick edge 7, 6. No cycle is formed. Include it. Using the previous table, we have to draw minimum spanning tree. For the table, 7 and 6 have a weight as 1. So we have to draw the minimum spanning tree using the vertex 7 and 6. Then pick edge 2, 8. No cycle is formed. Include it. Using the previous table, we have draw the minimum spanning tree for a table 8, 2 have a weight as 2. So we have to draw the minimum spanning tree using vertex 8, 2 and we have to check it is a acyclic graph. Then step 3, pick edge 6, 5. No cycle is formed. Included. Using the previous table, we have to draw the minimum spanning tree for a table 6, 5 have a weight as 2. We have to draw the minimum spanning tree using the vertex 6, 5 and we have to check it is acyclic. Then step 4, pick edge 0, 1. No cycle is formed. Included. For the table 0, 1 have a weight as 4. So far we have to draw the minimum spanning tree using the vertex 0, 1, and we have to check it says acyclic graph or not. Again, edge 2, 5 have a weight as 4. So we have to pick edge 2, 5. No cycle is found included. For the table, vertex 2 and 5 have to select for the minimum spanning tree, and we have to check it is a cycle or not. If any cycle is formed, the vertices are removed from the spanning tree. For the previous table, 6, 8 have a weight as 6, so we have to draw the minimum spanning tree using the vertex 6, 8. But here we have to form a cycle. So we have to omit the 6, 8 and then go to 2, 3 weight as 7. Draw the line. We have to check this cycle form or not. In 6, 7, pick the edge 7, 8 have a weight as 7. So we have to draw the minimum spanning tree in the vertex 7, 8. But here we have the cycle in the graph. So we have to avoid this vertexes and then move to 0, 7. 0, 7, its weight is 8. We have to draw the minimum spanning tree for 7, 8. Then step 8, pick edge 1, 2 from the previous table and it has a weight as 8. We have to draw the minimum spanning tree to the vertex 1, 2, but there will be a cycle formed in the spanning tree. So we have to avoid this edge and move to 3, 4. 3, 4 has a weight as 9. There is no cycle will be formed. We have to draw the minimum spanning tree in 3, 4. For the given example, the minimum spanning tree to get all the vertices and edges depend on its property. So no need to check the edges 5, 4, 1, 7, 3, 5. So the last minimum spanning tree values as 4 plus 8 plus 1 plus 2 plus 4 plus 2 plus 7 plus 9 equal to 37. Thank you.